So far, we discussed linear regression. Now, we'll be discussing logistic regression. In parallel, we'll be discussing logistic regression-based classification. One added piece of information is that logistic regression-based classification is suitable only for binary classification. That means in the data there can be only two class labels. Let's assume that we have this particular data set, where in the first column we have some level of blood factor, which are 10, 30, 45, 57, so on and so forth. And for these blood factors, in the second column, we have the labels, whether the person who has a 10 blood sample or 10 units of factor in the blood is a corona-infected patient or not. And we have yes or no labels in this part. Therefore, this first column is actually x1 in our linear regression model, and the second column is y. In our linear regression model, we cannot directly use yes or no. We will be using a number to represent yes or no. In this case, yes would refer to 1 and 0 would refer to no. That means yes indicates coronavirus positive and 0 indicates coronavirus negative. Now both the columns have numerical values. Now if we plot this data, that means in the horizontal axis if we put x1 and in the vertical axis if we put y, we receive this particular plot. Notice that in the horizontal axis we have this particular blood factor, and in the vertical axis we have either infected or not infected, that particular information. 0 indicates not infected and 1 indicates infected. 10, 0 is right here, 30, 0 is right here, 99, 1 is right here. Similarly, 87, 1 is right here, so on and so forth. So all these points are actually coming from this particular data set. Now consider that we want to build a linear regression model. That means we want to come up with a line that best fits the data. The line can be like this one, the line can be like this one, the line can be even like this one. Which line it should be, it depends on the analysis of those beta values. Obviously, in this case, since we have two columns, we will need beta naught and we'll need beta 1. Let's say that this line fits the data very well. That means this line will contain minimum amount of error from each point toward the line. Now notice that with this line, if we go for prediction and if our data contains a blood sample value with a factor of 120, the corresponding score will be very up in this direction, because this line, if you extend this line upward, somewhere it will be meeting here. So the value will not be very close to 1, rather it will be very, very far away from 1 in the positive direction. Similarly, if in a sample we find that the amount of that particular factor in blood is 30, then basically 30 is somewhere here. Therefore, the infected or not infected column will crisscross here. As a result, the predicted value, that means the y, will be far negative. So in a sense, we can say that if this line gives us a negative value for y, then for sure the sample should be treated as not coronavirus infected. That means negative. If we find a very, very, very large value, way greater than 1, then basically we can say that it's a positive sample. That means the patient is infected with coronavirus. But notice that there is a confusion zone in this area. If we have a blood sample with, let's say, 62 factor in the blood, so 62 will be somewhere very close to here, 62 crisscrosses here. So what should we consider? Again, this is just a drawing. We still don't know what our particular beta naught and beta 1 values are, so we don't know whether this line is a perfect one or not. Therefore, it is really difficult from a line to understand whether the data is speaking for a particular sample as positive, or is it supporting the new sample as a negative one. It would be more logical to create a probabilistic model where we can say whatever new sample we get, what is the probability that this new sample is coronavirus positive. To accomplish that, if we can convert this linear line to some sort of probability which varies from 0 to 1, then we can say that we have converted this linear regression line or linear equation to something probabilistic. If a patient has 50 units of some blood factor, then basically from 50 we will draw a line and we'll see where it hits the probability line. The probability line is very close to 0.19. Now we can say that the probability that the patient who has a factor unit of 50 in the blood sample has a probability of 0.19 to be considered as coronavirus infected. That means the probability is too low, so the patient is probably not a coronavirus infected patient. Similarly, if we find that a sample contains a blood factor amount of 70, then with 70 we draw this line and we see that the patient has around 0.83 probability of being infected. That means the patient is highly probable to be coronavirus infected. In a sense, we are saying that if we find that the probability is greater than 0.5, then we will declare the patient as infected. If we find that the probability is less than or equal to 0.5, we declare the patient as not infected. Now, where is that threshold to declare a patient as infected or not infected should be decided by a health professional or based on some other research which will include health professionals. Here, without any particular information, we are assuming that 0.5 is the threshold, but in practice this threshold might be changed by a domain expert. Now the question is, how do we convert this linear function to this probabilistic nonlinear line? Luckily, we already have an existing function in math or in statistics which is called a logit function that represents the exact same idea. For numbers which are negative, the function gives values very close to 0, and for large numbers which are positive, the function eventually gives numbers close to 1, and at 0 the function gives 0.5. Therefore, this spectrum varies from 0 to 1. As a result, we will be able to utilize this logit function as our probabilistic function for the linear model. This logit function helps us convert the linear combination of the independent variables to a logistic function model. Let's say that there is a way to compute beta naught and beta 1. The model parameters for this line would be beta naught and beta 1. That means our equation is y equals beta naught plus beta 1 x1. Of course, this column is y and this column is x1. And here all no's would indicate zeros, ones would indicate yes. Based on the logistic regression function we have here, we can write the probability that the person is infected. That means the probability that the person has 1 is equal to 1 divided by 1 plus e to the power minus beta naught plus beta 1 x1. In general, the function is the probability that the sample is positive or the sample is 1 is equal to 1 over 1 plus e to the power minus whatever linear regression model you have. If the linear regression model has many beta values, you will be able to incorporate all of them right here. So the general equation would be beta naught plus beta 1 x1 plus beta 2 x2 plus dot plus beta n xn. That means if your data has n plus 1 columns, then you will be using this particular equation. That means for this particular data set, this is our equation. If someone comes with a blood sample that has 45 units of factor, the probability that the person is infected is equal to 1 over 1 plus e to the power minus beta naught plus beta 1 times 45. If someone comes with a factor of 62, then the value would be 1 over 1 plus e to the power minus beta naught plus beta 1 times 62. So this value is actually the x1 value. If we already know beta naught and beta 1 for this particular line, then definitely we can come up with all these probabilities. You can compute the beta naught and beta 1 values using the linear regression class from scikit-learn in Python. Beta naught is the intercept and beta 1 is the coefficient with x1 that we discussed earlier with linear regression coding. There is also a logistic regression class with scikit-learn that can provide you these beta values. Let us say that we somehow retrieved the beta values using a package or a solver. Beta naught is equal to negative 7.9432 and beta 1 is equal to 0.1229. With this calculated beta naught and beta 1, we will be predicting whether a person is infected or not for any blood factor sample. For example, what is the probability that a person is infected given the sample has 45 factors? Basically, the equation would be 1 divided by 1 plus e to the power minus beta naught, which we already know, which is negative 7.9432 plus beta 1, which we already know, 0.1229 times x1. x1 here is 45. So we have 45 here. After pressing the buttons of a calculator, I find that the probability is 0.0822. That means if a person has a blood factor unit of 45, then the probability that the person is infected is this, which is pretty low and far below 0.5. As a result, the person is not considered as infected. Let's do a similar calculation with the value 62. The probability that the person is infected, if the person has an amount of 62 factor in the blood, is 1 divided by 1 plus e to the power negative 7.9432 plus 0.1229 times 62. After pressing the buttons of a calculator, we find that this is 0.4198. This indicates that if a person comes with a factor of 62 in the bloodstream, the probability that the person is infected is 0.4198. If our threshold is 0.5, this number 0.4198 is below the threshold. As a result, we declare that this person is not infected. I should mention that all the datasets I have used here in this video are fictitious data. They are not real data. Let's do these calculations for two more values. What is the probability that the person is infected with coronavirus if the blood factor contains 75.3 units? So let's plug in all the values we know. That means beta naught and beta 1 values and also the x1 value in this particular equation. Beta naught is negative 7.9432, beta 1 is 0.1229, and x1 is 75.3. The calculated value is 0.7877. Since this value is greater than 0.5, we consider this person as infected. For another value of 85.1, let's check if the person is infected. Obviously, the person will be infected because 85.1 is greater than 75.3, and with 75.3, the patient was infected. Therefore, with 85.1, the likelihood that the patient would be infected is high because our logistic regression function monotonically increases with higher value of independent variables. But still, let's do the calculation. After we do the calculation, we would see that the probability is quite high, 0.9252. Therefore, the person is infected with coronavirus. Logistic regression-based classification is very powerful. In real datasets, it has high accuracy. It is a binary classification mechanism. This classification technique relies on linear combination of the independent variables. It uses a standard logit function to convert the linear combinations to probabilities. The example we discussed in this video for logistic regression is basically a two-dimensional dataset. That's why you had beta naught and beta 1 in the logistic regression function. If you have a three-dimensional dataset, then you will need beta naught, beta 1, and beta 2. With a four-dimensional dataset where you have three independent variables and one dependent variable, in that case you will need beta naught, beta 1, beta 2, and beta 3. I hope the concept of logistic regression-based classification is clear now. I hope to see you in the next video.